questions, please put them in the questions box, and Errol, who will be helping me out, will go ahead and stop me with his questions, or we'll answer those at the end. I think that's pretty much about it. So let's go ahead and get started. My name is Rob Rallo. I'm a senior engineer at SunWize Power Battery, and I have been in the solar business doing off-grid systems for well over 25 years now. Quick background on SunWize. SunWize has been around for over 20 years in the off-grid market. We have a wide range of integrated systems, whether it be standalone, hybrid, battery backup, etc. We have sales offices throughout the country, and with several warehouse and manufacturing facilities around the country. And just some of the services we provide. Again, we provide integrated systems, we provide components, we can do distribution, we can do design services. If you need help specifying systems for a project, we can help you with that. Our systems can be ISO 9000 UL when they need to be, and also we do follow IEEE standards for system sizing. Okay. So again, just some of the services we provide. Just some photographs of some systems. Okay, let's get to today's agenda. One of the most important things to understand when understanding how a maximum power point tracker works is understand that the power, believe it or not, is dependent upon the temperature that the module is seeing, and this is very important, so we need to get that into detail. This also ends up affecting the voltage output of the 60-cell modules, which is why I've lumped that into this webinar. So you have to first understand how the temperature is going to affect the PV module, specifically the voltage, to understand how it's going to affect that output, specifically through the maximum power point tracker. So we're going to start off talking a lot about calculations and understanding the temperature effect. I'm going to apologize in advance. It's going to be a little bit dry, but I'll try to go through the calculations as quickly as possible. And if you want to go through those more detail on your own, you're more than welcome to. Okay, so it is very important to understand that the battery is charged by the current, not the voltage. So in general, you only need enough voltage to get the battery to the full charge. So let's say for a 12-volt battery, somewhere between 14.1 and 14.4 volts, it's all you need. Okay, you don't need anything more than that to charge the battery. It's actually being charged by the current. So the current is what charges the battery, not the voltage. It's important to understand that. If that voltage is not at least as high as that voltage, the battery will not be fully charged. Okay, so if you're, let's say it's only going to get 14 volts in the solar array, then your battery's only going to get charged that high, and that's not full charge. A full charge for a 12-volt battery should be between 14.1 and 14.4, and that doesn't include temperature compensation. So the next question is, well, if the battery only needs 14.1 to 14.4, then why are solar modules, why do they have such a high voltage? So for a 12-volt module, yet again, you'll see that the maximum power voltage is all the way, at 18 volts. I mean, typically PV modules have a max power voltage of 17 and 19 volts. The question is, so why do you then need such a high voltage if you only need, 14 to 14.5 volts to charge a battery? You have, almost an extra 4 volts that you don't need. Why would that be? And again, depends on the battery manufacturer. Again, somewhere between 14 and 14.4. So the reason is there are these losses you have to take into account. You can have line loss, which is basically voltage drops in the wires between the solar array and the battery. Okay, not just to the charge controller, but also the charge controller of the battery, so all the way through the process. And depending upon how you interpret the NEC, that could be between, the allowable by NEC can be between 3% and 5%. Okay, if it is the maximum of 5%, that's 0.6 volts on a 12-volt system. The charge controller themselves have a loss, and that depends on the type of charge controller you use, because it has diodes and transistors in there, depending upon those types of solid-state components. That can range anywhere between a half a volt and 1.2 volts. Okay, but the biggest voltage drop can come from the module itself. It can be up to 4 volts at 50 degrees Celsius. And that sounds pretty warm, but if you have systems in a warm climate like Texas, Florida, Arizona, and other places, it can get pretty warm, so that number isn't out of line. So if you add up all of those voltages, all of a sudden you have losses that can range between 1 and 5 volts, and all of a sudden that that 18-volt module we had is only 14 volts, which is pretty much the bare minimum you need to charge the battery. And that is why solar arrays have a higher voltage than is needed because of all these other things you have to take into account. So, and it's really important, again, to understand that you need to fully charge the battery. I'm going to come back to the number again between 14.0 or 1 and 14.4 volts. That's important to get the battery to 100% state of charge. Now, if you go to a lower voltage, you'll get the battery mostly charged, but not fully charged. And some people are going, well, do you really need to get the battery to full charge? Yes, you do. It should be fully charged at least once a month, preferably once every week or two. And that includes, in a solar system in the wintertime or whatever. I know that's not easy to do in December, but you really need to get batteries to a full state of charge. If they don't, if a lead-acid battery sits at a lower state of charge for an extended period of time, the battery will sulfate. Basically, sulfur crystals will form on the plates, and you'll lose capacity in the battery, and eventually will fail prematurely. We see this an awful lot. A battery manufacturer once told me batteries don't die, they're murdered because people aren't properly charging them. So it's very important to understand that you have to charge them properly, and that includes understanding the voltage losses from the solar module of the battery to make certain it gets properly charged. We're going to go through these calculations again, but it's important to understand that if your battery is not properly charged, if it is not fully charged to the voltage the battery manufacturer recommends, that it will sulfate, it will lose capacity, and that battery will fail prematurely. You should be able to get about 5 to 8 years out of a good high-quality solar battery. So if your battery is only lasting 1 to 2 years, and I hear this a lot, then that probably means there's a problem with your system. Either your charge set points aren't correct or there's something else going on. So, and most solar components should last 10 to 25 years. And again, your battery should last about 5 to 8. Batteries nowadays can be as high as 40% of the cost of the system. So it's the single most expensive component. So if you're not getting the maximum out of your batteries you can, you're wasting a lot of money. So just as an example, if if your system costs $5,000, 40% of that's about $2,000. So if you're replacing the batteries every 1 to 2 years because you're not getting that life you should out of them, you've pretty much wasted the cost of the system $5,000 in 5 years or more. So again, there's a lot of money you could be wasting here if you're not getting the maximum out of your batteries, and if you're not getting this 5 to 8 years, then you probably need to talk to somebody about what's wrong with it to try to fix that problem, because you should be able to get that. Again, a high quality solar battery. If you're using cheap batteries from Walmart, that's a whole other story. You're only going to get 1 to 2. Okay, so let's get into these calculations I mentioned earlier. And I'm going to use a SolarTech 140 watt module as an example. You can see the VOC, which is the maximum output voltage it can have. That's what we call open circuit voltage. Maximum voltage is going to be 22.2. That's at STC, and I'm going to talk about these ratings in a minute. STC is a lab test rating, and I'll get in that in just a moment. The maximum power point, and that's the point at which the solar module produces the maximum power, is at 18.3 volts at STC. The temperature coefficient for this particular module, and you'll notice all modules have all these specs. So on the right side is basically the specs right from the spec sheet for the module. So I'm taking this directly from there. This is nothing I made up. It comes directly from the module manufacturer. Temperature coefficient is going to be minus 0.36% per degree C for the voltage at STC. Now, the other thing to note here is normal operating cell temperature, that's NOCT, is 48 degrees. Okay, that's going to be very important, and I'll explain that to you in a moment just why. But let's first talk about these different ratings. STC stands for Standard Test Conditions. This is kind of a lab condition. Okay, it's 1,000 watts per meter squared of sunlight. That's the solar insolation or solar irradiation. That's the amount of sunlight that actually hits the module. Spectrum, which is basically an air mass of 1.5, and a cell temperature of 25 degrees C. The important number here is the cell temperature of 25 degrees C. Now you'll notice NOCT is more real world. It is, STC again is lab conditions that you will probably almost never find in reality. I think the only place I ever see anything like that is in Colorado because of the altitude they're at and because of the cooler temperatures. So NOCT is more reality, more real life, what you're going to see. You're going to see that, you can see that the array, the amount of sunlight you're going to get is already reduced to 800 watts. So you've already reduced 20%. So basically that max power you were getting out of your module is really only about 80% of the rating in reality. Okay, you're going to notice the ambient temperature of 20 degrees C and a slight wind of 1 meter per second. The key here is ambient temperature. Notice the STC is at cell temperature and the NOCT as at ambient temperature. So if you look at those two things all of a sudden, you start realizing that there's a huge disconnect between cell temperature and ambient temperature. Okay, so if you look at that, you're going to go, okay, well the cell temperature NOCT is actually 48 C with an ambient temperature of 20 degrees C. Remember that NOCT is at 20 degrees C of ambient. Okay, so there's actually a 28 degree delta between the cell temperature, which is 25 degrees C, and at STC, and the cell temperature of 48 degrees C at NOCT. So if you were to take that delta and apply that to NOCT ratings, that actually ends up being a cell temperature of -3 degrees C at STC. I don't think most people are actually operating their solar modules at -3 degrees C. So all of a sudden you start realizing that temperature becomes a problem because they've started calculating temperature at below freezing, which is not normal for most solar systems. Granted, it can happen in the wintertime up north, but most systems do not operate at below freezing the majority of the time. So this is why temperature becomes a big factor. So now let's get into some of these calculations and understand just how it does affect it, realizing that there's a big disconnect between the module rating and what we actually get in reality. So taking that VOC number we had before, the 22.2, multiply that by the temperature coefficient we actually get a number of 0.0799 volts per degree cell. I'm going to go ahead and run this at an ambient of 50 degrees C. I know it's a warmer one. I'll run some other ones at colder temperatures too, but just to kind of give you an idea of just the impact this temperature can have. So at 50 degrees C, the cell temperature is actually 78 degrees C. That's pretty high. So if you subtract that from the 25 degrees C, which is STC numbers, you get a delta of 53 degrees C. You multiply that by the number we had above for the temperature coefficient, and now you have a voltage drop of 4.23 volts. It's also important to note these are negative. The temperature coefficient is a negative number. So that voltage is subtracted from the VOC or the maximum power voltage. So all of a sudden, at 50 degrees C, you add that to your maximum power voltage, you're now at about 14 volts. Okay, your VOC is at 18 volts, but your maximum power point is now at 14 volts. That's before any other losses. So all of a sudden you start to see that, geez, my battery wants to get charged at 14.1, my maximum power point is at 14.0, I'm barely getting my battery charged. So all of a sudden this temperature becomes important and it could perhaps be an issue. Now, this really comes into play. Remember, that was for a 12-volt module we ran those calculations for. Let's run the calculations for a 60-cell module, because some people try to use a single 60-cell module in a 24-volt system, and they don't really get the battery fully charged. And we're going to go through the calculations very quickly to understand why. And again, we're going to go ahead and run the same exact calculations you just did. You'll notice that we're looking at an STC number for a 265-watt module. The open circuit voltage is 37.7 volts. And here's the NOCT numbers. And again, you have the temperature coefficient of minus 0.31% for VOC. And your normal operating cell temperature here is about 45. 45 is normal. Sometimes you'll see them as high as 48, but 45 is the normal operating cell temperature for a module. Okay, so if we go through those calculations again, multiplying the VOC by the temperature coefficient number, we get a minus 0.117 volts per degree C. Using that 50 degrees C, again, this is for warmer climates. Okay, the cell temperature is 75. We go through the calculations again. You have a 50 degree delta. Multiply that by the 0.117, and now we have a minus 5.85 volts. Okay, so we add that to the maximum power voltage, and all of a sudden your maximum power voltage is now at 24.7 volts before any other losses. And that's for a 24-volt battery. So that's pretty much nominal voltage. That's not going to charge your battery. If you add that to the Even if you look at the VOC number, the VOC number is low too. So you can see now why using a 60 cell module with to charge use a single 60 cell module to charge a 24 volt battery won't work. You'll never get it to the maximum charge voltage that the battery wants. Just can't happen. The battery needs to be at least 28 volts, and you have a maximum power point now of 24 volts. So just not enough voltage and current to get the battery charged. So we don't recommend that. Now I'm going to talk about, if you do want to use 60 cell modules, how you can charge the battery with it. I'll talk about that when I get into the advantages of maximum power point tracker. That's where it can help, but you need to put 2 of these in series to do it. One isn't enough, you'd have to have 2. Okay. I'm going to talk about this briefly because I don't think anybody's doing this anymore, but many years ago, about 2 decades ago, somebody had a bright idea that, hey, we can take advantage of this temperature effect and we can get into what they call a, quote, self-regulating module. So we don't need a charge controller. Well, it only worked for warm climates. It didn't work so well. There were other factors that had to be involved in it, and it certainly didn't work when it got cold. They would overcharge the batteries and damage them. But they're trying to take this temperature effect into account, also realizing that the batteries have a temperature compensation adjustment as well. The problem is that the battery temperature correction and the module temperature correction aren't always the same, and that's what created issues. So I will mention a little bit more about battery temp comp when I start talking about the MPPT calculations, because those come into play when factoring what the performance between the MPPT and the PWM charge controller is going to be. But I just wanted to talk about this briefly because I think some people looked at that and go, geez, we could take advantage of this temperature correction factor on the module, and maybe if we can match up the the right number of cells such that we're not overcharging the battery, maybe we can get this just right. Well, not quite so simple and easy, and again, that temperature correction factor on the battery isn't exactly the same as on the modules. And then again, it only worked in warm climates barely. So that's enough about self-regulating modules, and which is why I don't see them anymore either. They haven't been around for about a decade because of that. And again, this is a little bit more on the curves on that. I'll talk more about the curves in a little bit when we get to the MPPT charge controller ratings. Okay, so let's start on that right now. MPPT versus PWM calculations. So using again, using a nominal 24 volt module, this is a 72 cell module. I'm going to go ahead and use the 320 watter. And again, we're going to go through the same exact calculations we've been going through before. And again, if you want to go through some more detail, feel free to go back and review this webinar again and grab a calculator, use whatever module you want. You can go ahead and go through the same thing. All the information you need should be on a module spec sheet. If it's not on a module spec sheet, contact the module manufacturer because it should be on there. Okay, and just usual new numbers again. So let's start with the calculations for the MPPT charge controller. So because of the fact we are calculating wattage now, not voltage, and actually I'm going to point this out. You'll notice that the one thing I'll point out real fast before we get into that is that you'll notice the temperature coefficient for max power actually is even worse than the temperature coefficient for the voltage. Temperature coefficient for the voltage is only minus 0.31, but for the power it's actually minus 0.41. So the power actually degrades even faster than the voltage under temperature. And this is the thing that makes the performance of an MPPT not be as good as we think it is. And actually, before we even get started on that, let's just do a quick poll just to see what people think we're going to get. So before we start doing these calculations, let's see how people think the performance between the MPPT is going to compare to the PWM. So let's give people a few minutes to vote, and let's just see how much more power people think they're going to get out of the MPPT versus the PWM. Okay, we got about a little bit over 50%. Okay, 63%. Okay, good enough. Okay, so it looks like the majority of the people have got it right, and you're going to get between 5 and 10%. So about half the people have gotten it right. You're going to get between 5 and 10%. Okay, and I want to show you when you're going to get 5, when you're going to get to 10, and we're going to go ahead and go through all of those things right now. So let's go to the next slide where we can go through the calculations. And again, pointing out that we're going to be using the wattage now and the wattage temperature coefficient. You're going to get a wattage number now of minus 1.312 watts per degree C. So think about that now. That is over a watt per degree C. That's pretty substantial. So if you have an ambient temperature of 50 degrees C, now again, this is because this is all temperature based, I'm going to be using the high numbers. I will do additional calculations at all kinds of temperatures just really fast so you guys can see the different type of effect at different temperatures. And again, you're welcome to run these whatever temperatures you want for whatever module, wattage, or everything else later on your own if you like. Okay, so taking into account cell temperature 75C, we're going to have a reduction of minus 32.8 watts. So that's going to take our 320 watt module down to 287.2 watts. Errol, is my screen coming up okay? Okay. I just blipped
yes,
for
it is. Sorry, I was on mute. Okay. Yeah, it looks fine.
Sorry. Okay, thank you. I'm sorry, I just blipped for a minute. I want to make sure we're okay. Sorry about that. Technical difficulty. Okay, so this is going to get into temperature compensation of the battery. I mentioned that before, and we have a couple of handouts for you right now that you can get. We have a couple of handouts that are up on along with the presentation. One of them is the battery temperature correction. Battery temperature compensation. It's a whole little hand on that. You can go through these calculations on your own and understand why you have to adjust the battery voltage. We have a whole tech note on that. The other one's on shading. We're going to talk about that later on. We talk about how the MPPT can help shading or not. So that's going to be on that as well. But just so you understand, if you want to get into more detail on battery temperature compensation, if there's a handout on that, you can read that at your leisure. But basically, to sum it up really fast, the battery does not need to get charged at a lower voltage at higher temperatures. So if we're to go ahead and go through the battery calculations, that 24 volt battery really needs to be charged about 27.66 volts at high temperature. Okay, so if we look at that, so we divide simple math at this point, we're just going to divide the wattage we got, divided by the battery voltage, we're going to get current. Now keep in mind, this doesn't include any of the losses to the charge controller. Okay, this is under ideal conditions because you know there's going to be some losses to the charge controller in some form. They're about 95% efficient, but again, there's going to be some loss through there. I have not taken that into account at all. So we're going to get a current at the battery. Again, this is a charge current to the battery of 10.38 amps, and this is under best conditions because I've assumed no losses. Now let's go ahead and run those same calculations for a PWM controller. Now what's happening here is that the temperature actually increases the current. And I'll show I'll go over that and then a IV curve in a minute on a solar module. But the current actually goes up with temperature. Although the voltage and power go down, the current actually goes up. So we're actually going to get a small increase. It's very small though, as you can see. It's 0.005 basically amps per degree C, which is quite a bit different than the whole watt per degree C we were losing with the power. We're actually gaining just a little bit of the current. So we're going to go ahead and get those calculations again. So we're actually going to get about 0.2 of an amp in this situation. Gives us a total of about 9.5. So if we subtract the 9.5 from the 10.38, that 10.38 we got from the MPPT, the 9.5 is the charge current we get from PWM. That gives us a delta of about 0.88 amps or an 8% increase. So there you go. So your MPPT actually increased your production to your battery of about 8%. So not quite the 25 to 30 that some people, or 20 that some people think you might get, or that some people claim. Okay, and again, this all comes back to the temperature that the module is seeing. So you're going, well, geez, 50 degrees C isn't really reality. It's fine for, say, Florida, Texas, Arizona. Let's go ahead and run these calculations at a more normal temperature of 25 degrees C, which is 77 degrees Fahrenheit, which is pretty normal for most people, and they get pretty normal temperature. So let's go ahead and do that, and we're going to do this real quick again. Again, you can break it down in more detail later if you want. So now your max power wattage is 303. Your battery charge voltage is 28.56, which is pretty much what it should be at 25C anyway. So I've done the temp calcs there because temp calcs are based upon 25C. Let's see. So that's going to give you 10.63 amps. You'll notice you're going to get more power out of, you're going to get more current out of the MPPT now, and you're going to get 9.38. So this is actually going to give you a little bit better. So again, this proves again at colder temperatures, you're going to get a little bit more out. This is the 11% you're going to get. So this is, I was saying, 5 to 10. this is kind of that 10 range. Okay, and again, this kind of really depends on the temperature coefficient of the module, so the different modules are going to have different outputs, but generally they're all going to be in the 5 to 10% range, depending upon the temperature coefficients, the temperatures you're working at, sunlight conditions. That's the other thing I'm going to mention in a second. Sunlight conditions are also going to have an impact on that. So we're going to go ahead and do that in just a minute. But before we get to that, let's get these STC conditions. So basically, STC is basically an ambient of about 0 degrees, which is freezing, which is under ideal conditions. You're going to see even under that, you're still going to get 15%. So even under the best conditions, you've got basically lab conditions, this and the other, it's still only 15, which is nowhere near the 20, 25, or 30 that some people claim. So again, 15 is the absolute best you can ever get under the best circumstances. Now, and again, these are all based upon 100% sun, which you're never going to get in reality. So if we actually run these on NOCT, which is more reality, you're going to get 80% of the sunlight. You're going to get, it's got that ambient of 20 degrees C, yada, yada, yada. You go through all the calculations again, and you're going to see you're going to get about 7%, which is a good average. So I'd say on average, you're going to get around 7. So that kind of gives you an idea of what you can actually expect to get out of an MPPT controller. Somewhere between 5 and 100, 5 and 10, and averaging about 7%. Okay? And you all want to double check my numbers, please feel free. Okay, getting back to these IV curves just for a minute might help a little bit. If you look at the IV curves again, the neat thing is you'll see that the voltage doesn't change much based upon sunlight conditions, but you can see that the current output is very linear, as I mentioned before. So, I mean, the voltage is varying very, very little. I mean, the voltage is varying by just a few volts. Whereas with the temperature, it varies dramatically. You can see the voltage varying by almost 10 degrees between 5C and 65C. But you can see the current doesn't vary much, just a little bit. You'll notice, again, at the higher temperature, the current's a little higher, but not much. So just keep that in mind. Now, the other thing, getting back to, again, what's most important to the batteries? Current. So you also want to keep that in mind, that that's what you're looking for. So, so actually, even though most people use the max power current for doing calculations, for charging the batteries, the reality is you're usually going to get higher than that, which is why you're usually going to be operating a little higher than that because your voltage is a little less. Usually your battery voltage is a little lower than your max power voltage. That's what you want for proper charging the batteries. So usually your current's going to be a little higher than your max power point because of these curves. Looking at these IV curves, you'll see that where the knee is, you're going to shift that voltage back, and your current goes up. I bring that up because I did our previous webinar was on trying to size charge controllers, and all the numbers for sizing charge controllers were based upon short circuit current, not based upon max current, and that's exactly why. Because when you're actually charging the batteries, especially bulk charging the batteries or battery or low voltage, you're actually operating a little bit closer to that ISC instead of that IMP numbers. Just something to keep in mind. And if you want more information on sizing a charge controller and those types of things, I would recommend reviewing the previous webinar we did last month on charge controller types and how to size them. That's up on the SunWize website for you to review if you like. Okay, so if the output from an MPPT controller is only about 5% to 10% more, and the MPPT controllers can cost 2 to 3 times as much as a PWM, then why would you want to use an MPPT? I mean, solar modules have gotten so cheap now, it's cheaper just to go ahead and add more solar than it is to use an MPPT. Oh, I should have done this beforehand. Let's go ahead and let's do this. I'm going to do another poll real quick on if doing a quick poll just to see what people think with regards to the charge algorithms and the features of an MPPT. Some people think that those are better than a PWM, so let's see how many people think they're better or not. See, about 30% of the people voted. We'll give this a little bit longer so you can get to 50%. Okay, a little better than half. Okay, it looks like it's about 50-50, but it looks like more of you think you're going to have more advanced features in the MPPT than the PWM. It's going to have more advanced charging. Let me go ahead and share this for you guys to see. The answer is they're really not. Those that said they don't really have any advanced features is true. Um, they've always generally used the same charge algorithms because they both have similar circuitry. So they use the same charge algorithms. So there's really no advantage there in terms of some of the other features, like in the some of the first MPPTs had additional features that weren't in the PWMs, like they may have communications and things like that. Most of the newer PWM controllers actually have a lot of those too. So the newer controller, the new PWMs have pretty much a lot of the same features and functions as the MPPT, and they have the same charge control algorithm. So you gain nothing there either. So you've gained not you've gained a little bit in performance, but for a higher, dramatically higher price. You haven't gained much in terms of features and functionality. Again, I mean, the PWMs, some of the newer ones have adjustable set points. They got meters, remote communications, lighting control, etc. So a lot of those same things that you saw in the MPPTs are now available in most of the newer PWMs. So why would you want to use one if it costs that much more? Well, sometimes that 5 to 10% matters. Especially in the winter, you might need a little bit extra. Might be space limitations. Some people might want to trailer mount these so they can make them portable and move them around, or they might want to attach it to the side of a shelter. So sometimes you might need that little extra, so that might matter in that case. Sometimes under certain conditions, the MPPT can extract more energy. In low light conditions, it can do that. Sometimes with some clouds. I mentioned shading before. Depending upon the type of charge controller, the MPPT controller, and the type of algorithm it has, shading may or may not be better for it. And if you want to get into partial shading versus hard shading, there's also a little tech note for shading as well. You can look into that. But as I understand it from some of the manufacturers, that if you have a soft shading, which can be caused by kind of dust and stuff like that, that the MPPT can help. But if you've got a hard shadow from a pole that might be in front of it or something like that, or I don't know, something like that, if somebody accidentally mounted a tower in front, that it's not going to help you, and that actually that some of the charge algorithms can actually, the MPPT algorithms, excuse me, can get confused and actually make it worse. So depending upon your shading problem, it may or may not be a help actually. And again, if your ray is not at an optimum tilt or orientation, if for some reason you had to orient it a little bit off the south, the MPPT can help you a little bit more there. So again, it just kind of depends on the situation, the conditions, and your application as to whether that can be of help or not. Now, where I like to use it is my best. I like the best feature of this is, and this gets all the way back around to the 60-cell modules again, is you can use 60-cell modules to charge batteries. If it's a 12 volt, you only need one module in series. If you have 24 volts, then you would need two. For 48 volts, you use three. So the neat thing is you can wire the array at a higher voltage to charge the batteries. This has other advantages too. On a nominal 12 volt module, which is 36 cells, or a nominal 24 volt module, which is 72 cells, you can wire these in series, and you can reduce the number of output cables you have, or the number of inputs into your box. Basically, you could perhaps eliminate a combiner box and save some money. So if you can reduce your cables and reduce some circuit breakers or combiner box, you can save some money there. If you have a voltage drop problem, this is especially true on 12 volt systems. If you might have several solar modules up on a pole and a battery box far away, if you're running 50 feet or 60 feet on a 12 volt system, that's a lot of voltage drop to worry about, and you might have a problem. Well, if you can run that array, if you've got 2 or 3 or 4 modules, you can wire those all in series, and then that voltage drop isn't a problem. You can reduce the current by that much. So instead of, if it's 4 modules, your current's now a quarter would have been at 12 volts at 48 volts. Plus the voltage drop isn't again as big an issue because now you have more voltage to work with. So you have 2 advantages of that. So there are some advantages to using it. As a matter of fact, again, this being able to wire the array at a higher voltage is probably the single most important reason I actually use an MPPT. And it can really be a huge advantage in these 12 volt systems. So even though it costs more money, there may be applications of which it makes sense. Now, some of the advantages of a PWM, again, it's lower cost. As I pointed out, it can be, again, the MPPT is 2 or 3 times the cost. It is simpler. Because it's simpler and has less parts, they're generally more reliable than that. Also has less heat dissipation. And just look at the heatsink on a PWM controller versus an MPPT. You'll notice that the heatsink on an MPPT is like twice as big or bigger on a PWM. So if you're in a sealed box, it's something you have to think about. Now you have more heat being generated. You have to get that heat out of it, or you get that box even hotter. And because you have a bigger heatsink, it's also going to be bigger in size. The PWMs are usually smaller. Again, if you're going to put this in a box outside, then you may have to pay more money for a bigger box to be able to accommodate that. So you might want to think about that as well, that you might have a heat problem, and the size might be an issue as well. So the PWM has its advantages there. So to summarize here, temperature has a huge impact on the PV module output voltage and power. And again, I think we've more than covered that with those calculations. 60-cell modules, a single one doesn't have enough voltage to recharge 24-volt batteries. I think we've proven that pretty well. And I think we've covered some of the reasons why you want to use an MPPT and some of the advantages of a PWM. So, and again, please feel free to use all of those calculations to verify and double check everything I've been doing. And if you've got any type of concerns, you can go ahead and go back through these and run it for your system and see whether you have enough voltage to charge your battery or not. So I have one last polling question, everybody, and then we're going to go ahead and get into some questions. And the next polling question is, what would you guys like to see next? So our last webinar was on different types of charge controllers and how to size them. This one, coming out of that one, we had a lot of questions. We thought it would be worth doing a whole webinar on MPPT versus PWM because we had a lot of questions on that. So so let's see what topics y'all would like to see for next time. Let's see, I got about half the people voted. Got this go just a little bit longer. Okay, it looks like a lot of people want to see the off-grid system design, how to size that and design it. A lot of people want that. A lot of people also want remote power, so remote communications these sites too. So we go ahead and share this, everybody. So yeah, I think a lot of people looking forward to the design one. We're going to try to go ahead and have the off-grid system design. We'll both do a basic and advanced. We're going to try to do that probably late February, early March at this point. I'm still working on that one. And the remote monitoring, we could probably do that one a little bit sooner, so we'll put that together for you guys too, and perhaps we can have that as early as next month. So let's go ahead and take questions. Again, please type your questions in the question box. Errol?
Yeah, we got a few. I'll start going over a couple of them here, and then if other people have more, I see a couple more coming in, I encourage you guys to utilize the chat box. So we've got about 20 minutes left on the last one. I think we went right to the end with various questions from folks. So I'm going to start off with a question from Peter Martin on, is there a type of charger that can work to desulfate a battery or help a damaged battery? I have not heard of such a thing, I don't believe. Rob, do you want to speak on that?
Actually, there's a device called, and I've actually worked with these before. There is a device that actually has a high-frequency pulse that pulses the batteries that can help break them up.
Right.
My experience has been they can help a little bit, but some of these new charge regulators, the PWMs are working at a higher frequency anyway, and so are the MPPTs. So both of those were used a lot when we were doing it. Again, I'll come back to the previous webinar we had on the charge controller types. When you look at the shunt regulators and the series regulators, those were just on-off type charge controllers. They weren't high frequency or the low frequency. So that was a bit of a problem with that. So they had this thing that actually did a high frequency pulse that would break that up. The PWM and MPPTs are already kind of a higher frequency, so those people don't use it as much anymore because they're not really needed. So those are, again, that's what they would do, was that high frequency thing. But again, that's not really needed because we're already operating at a higher frequency with the PWM and MPPT. So you don't see people really using this a lot too much anymore for that. They're very popular about 10 years ago. Again, we had a lot of the on-off type charge regulators.
All right, we got another question from Austin about the performance change in extremely cold climates such as Canada. I know we covered down to 0C. I advised that we can basically use the same calculations to figure out what that would be, what the performance increase would be in very specific conditions. But at a certain point, you're going to be running up against concerns about your battery freezing and other things like that at those extremely low temperatures. But you will eke out a little bit more as you continue to drop in that temperature until you reach your critical. Rob, do you want to add more to that?
Yeah. Yeah, I think you're probably looking at the max of 15, but again, it depends on the conditions. I think you're most likely going to probably see 10 for the most part. 15 might be possible, but again, it depends on the sunlight conditions and some other things. Let's put it this way, I wouldn't design for that. I wouldn't design on that and count on that. That's the thing that have to be a problem, is that the reason some of these systems fail is people are designing systems thinking they're going to get 20 or 30% extra out of it, and it's not. When you only see you're getting 5 or 10%, and you've sized it so you design your system so you're going to get 20 or 30, your system's going to fail. You have no design safety margin anymore. That's one of the reasons to have this conversation is that, if you're not getting that much more out, you can't add that in. So you have to, if you're designing you're designing your system based upon this power you think you're going to get, you're not, then your system's going to fail prematurely. And you're going to destroy those batteries, as we talked about earlier.
All right, we got another question from Scott Williams about the reliability differences between PWM and MPPT controllers. I know we touched on this very briefly in the last presentation due to the MPPT's additional components and additional complexity. Rob, do you want to speak to that?
I would defer to the manufacturer of those. I know several of them have told me that and again, all of these charge controllers are very reliable anyway for the most part. Most of them have decent warranties, but if you just think about it from the number of parts perspective, there's a greater risk just based upon that and there's greater complexity there. So just based upon that, in general, you're going to find the MPPT is going to have a slightly higher component failure rate than a PWM.
Question from same gentleman about noise for RF on MPPT versus PWM.
Well, they both have the same problem because they've both got that high frequency thing going on. I will say this though, on the PWMs you can actually disable that. A lot of the PWMs have a feature. It depends on the manufacturer, but some of them have a feature and option that allow you to drop it into that low frequency mode if there is a noise issue.
Okay.
So actually, I'd actually recommend the PWM over the MPPT for that reason. You can't do that on the MPPT because you have to operate at that high frequency in order for it to work right. If you're not doing that, then you can't actually do the MPPT. So the MPPT actually doesn't have that option. It has to be that in order for it to work. So again, if you're in that situation, you're better off with a PWM type that you can then convert to a low frequency one. So yeah, so that's an option. Again, it depends on the manufacturer of that unit you're using.
Okay. I got a question here from Peter Martin about solar battery recycling to include recovery and continued use. Within the context of the solar battery recycling program that we were referring to, that is not for recovery and reuse. That is simply for disposal and credit and easy pickup and coordination from the logistics of various battery manufacturers. I don't know of any sort of reuse or recycling programs for reuse of lead-acid batteries afterwards, although certainly depending on the quality of the batteries, there might still be some life in them. I have a question on 60 cell versus 72 cell. I'm not sure what this was specifically with regards to. Perhaps you could elaborate. I don't know if that's just a general question about which is preferred to use.
For me, in off-grid systems, I mean, the 72 cell modules now, $1 per watt, are almost about the same as a 60 cell. So I don't see any advantage using a 60 cell whatsoever. The 60 cell forces you to use an MPPT. Now, the 72 cell module can be used with a PWM to charge a 24-volt battery. You can also use a 72 cell module to charge a 12-volt battery with the maximum power point tracker. So if you're using a 72 cell module, you can use it with a pulse width modulated unit to charge a 24-volt battery, no problem. They're designed for that, which are great. If you want to use it at 12 volt, you can with an MPPT. And again, I mean, given the price between the 60 and the 72 cell, the dollar per watt is about the same. I much prefer to use a 72 cell on a 24-volt system in most cases. It's just more cost effective generally.
Yeah, agree with that. All right. Question from Peter Martin: does higher frequency damage the lead plated through vibration? So can the higher frequency of the charge controllers actually have a negative effect on the battery through the plates and vibration?
Oh no, no, not at all, not at all. And actually, the neat thing about a battery is there's kind of a capacitance to them because of the plates. They work like giant capacitors. It's kind of like a filter actually, and it's actually very good for surges. I always laugh. People worried about surge protection on batteries, and I'm like, why? It is a giant filter. It's its own surge protection basically. So no, not because of the capacitive effect. No, that's not a problem.
Okay. Question from Scott Williams: are there any noise filters for MPPT charge controllers?
You can. I'm certain. I'm not. I've done this before. You would put the filter on the load side, so I'm not thinking of it more for the MPPT or for the battery. I'm thinking it more for the load. And yes, you can put a filter for that on the load side. That is possible. I've actually sourced those before and had to do that before for people that had very sensitive equipment. But when you go through all of that, instead, you'd be better off just use a different system design. To be honest, it's more cost effective. It gets back to that cost thing. I'm going to pay more for an MPPT charge controller than I have to put a filter in there. It would, in my opinion, it would be more cost effective just to use a PWM unit and then convert it to low frequency. It'd be more cost effective. But yes, if you have something you have to retrofit because of that and you're stuck with 60 cell modules and that type of situation, then yes, there are filters available. You have to know a little bit about the load though in order to do that, so that you don't have a problem. You have to know the current and the voltages and stuff like that in order to make certain that filter is matched correctly to that load.
Okay, thanks, Rob. All right, I think I hit everybody's questions. If there was an outstanding question that somebody wanted answered that I didn't get to, please repeat it in the chat box. We'll give people a few more moments to get anything else out that might be on their minds. If there's nothing else, then thank you everybody for joining the webinar. And we'll definitely be hosting for sure the basic off-grid sizing, the advanced off-grid sizing, and the remote monitoring for off-grid power systems within the next couple or several months for sure. Hopefully sooner rather than later, but we'll definitely be doing those three for sure. So.
Okay, thank you everybody.
All right, don't see any more questions. I think that's good.
Okay, well then this concludes our webinar, and we look forward to having you join us on our next webinar next month.
Thanks everybody.